listen, we're going to have to throw you in jail because you don't have a passport. We'll send you back. He looked the officer in the face and he said, Mr. Officer, when I was living here, you didn't give me a visa. How is it that you expect me to come back with a visa? And the big guy, he almost fell through the floor. It's like, huh? And he just, and then of course, thought it was, all right, how long are you going to be staying? Don't ask me. This was, I think it was carried by some papers. It was a classic. I can't remember when that happened. So anyway, but that's something about citizenship and passport and all the other stuff. What it boils down to in this system is not just saying I'm an American. America, you got to know what America is. America is a marriage between especially the Ivy Leagues.
But would you begin from the top as to what the education system is?
Yes, well, the America as a country, okay, is a marriage, okay, between the universities, which includes all the educational systems, because you got to go from the lowest level to get to the university. On the one hand, okay, that means we're talking specifically, particularly about the Ivy Leagues, your Harvards, your Cornell, your Princetons, and on the West Coast, you don't call them Ivy League, but the Caltechs and Stanfords and Berkeleys. Okay, and in the Midwest you have the Purdue's and the University of Michigan on the one hand. And then the Fortune 500 on the other side. That two systems come together and they marry. That's what you have. What's called America. And within that marriage, there are children that are brought up. Children could be human, there could be other things as well, but particularly human. So this product of that marriage are meant to inherit the goodies that is produced from this marriage. Okay, the goodies. Okay? There cannot be a Boeing without an MIT. See, Boeing does not exist without MIT. Okay? So, and then a job that is created in Boeing or GM or General Electric and so on, okay, has a corresponding qualification that's coming out of MIT that's going to take up that job. Okay? Now, but it is for the children of the marriage. That's the difference. That's what citizenship thing is all about, the children of the marriage. So, you got to remember that as that was developing, we were considered property. So you were not children of the marriage. So, I mean, you were, we were handed over along with the other products to the children of the marriage. Okay, thank you. So on that basis, you got to know the deal. You got to be clear about that. Now, what I just stated is simply a statement of fact. There's no exaggeration or twist or anything like that. That's the bottom line. So now, that means a European American, you know, who came from the founding fathers, as is spoken, and all that, whatever degree they earn has an equivalent job that's created in the industrial sector for them. They're not supposed to have unemployment. Okay? So it is the leftovers from that situation that the rest of us struggle for. Okay? Leftover. So when they're talking about 6% unemployment rate for whatever, you know, ours is so different. Somebody said the other day, something like twice. That's an understatement. If you hear the real figure, you'll be shocked. It's more like 70%. 70%. 70, that's correct. Because you don't have a Fortune 500. You do not have a Fortune 500, nor do you have those institutions. You don't have any Ivy League. And Harvard, since its inception, has been employing the founding fathers' children over and over. That is one certainty that they don't have unemployment. As long as Harvard exists, those people don't have jobs in Harvard. You want to push affirmative action over there, they have a number that is allocated. And that number is actually massaged through planning, careful planning. It has something to do with the special ed. It has something to do with your admission, because you have to have what they call qualifications, right? Yeah, you got to have qualifications. But if you're a special ed, how are you going to have qualifications to be in Harvard, to be a professor in Harvard? Harvard Math Department does not, you know, the last couple of years that I've been watching there, not a single black professor there, but you can't really blame them. So this is, I think, the mistake that's made. You know, people go jump and say, well, gee, well, we supposed to, no, wait. They planned, they sat down and they planned, and we had Timbuktu, of course, but Timbuktu is in shambles. Okay, so it's important. Okay, you know, that piece, and I don't want to dwell on it because we have work to do here, but that's within the unified field. But it's important to mention that because what's going on here is our own equivalent of Harvard. It is not below Harvard in any standards that you look at it. But as you can see, you know, this is our class. This is, you know, what you see here, this is it. Okay? I mean, at least for this area here. I have a little thing, you know, also on Long Island, but certainly not on the scale that Harvard is situated. So they, you know, had to plan, and that's what the unified field. They had to plan to say, okay, maybe those of us who are gathered here right now don't, you know, are not fortunate to have that, okay? You know, a university where you could, you know, certainly start studying and getting a degree to become a professor in for certain. Okay, you can plan on it. You know, a young kid on Long Island comes to tell me he wants to know about GAGUT, a white kid, because he wants to be a professor. Now, he's just getting into high school. Okay, he wants to be a professor. I don't know that the average black kid can say that. Wait, you're a professor in where? Howard is not our university. Lincoln is not. Somebody built it and said, well, you have it. That's still not yours. Okay? And we know that, those of you who study history knows, the development of Howard, okay? Okay? And so on and so forth. So, but you can take a good, clear look at things, or you can take a blurred view at things and just operate. GAGUT says you're better off looking at it from a clear vision, which is transformation. You transform, rather than struggling from here, trying to look at the thing behind the thing of this. GAGUT said, well, this is a transformation. You transform right here with these, and you look. You can see very clearly. Okay? So, that's what we're talking about. So, again, it's about geometry. Okay? Geometry. And in the geometry, we're talking about spaces, about curves. That's the geometry. Okay? That could be taken as a section of a more complicated three-dimensional space curve. And by the way, the jobs that I was talking about in the Fortune 500 that is created for a European-born American, primarily, from the Ivy League and all the other places, institutions. On the bachelor's level, those people come in and they work with the, junior managers or whatever, or supervisors, with the technical people, okay? And the other staff, okay? In the learning process. Now, in the process of production, once in a while a challenge is reached, okay? You come across a challenge. How do you do this molding? What's the scientific basis of this process here? And so a need arises in terms of, well, let's research it. Let's look into it. Let's see how that process can be done. So, two minds come together, one from that industrial sector and the one in the university. So, well, this young man here just finished a bachelor's degree. We could cheaply employ him to look at the nature of that process and pay him cheaply in terms of tuition, money, and stipend, okay? Plus a promise of a master's certificate, okay? That's a great deal. So he says, wow, I'll take it. So that's very economical compared to the company trying to hire somebody that, on a professional level over there that will do this research. You get a cheap way to do that research. And the young man is pretty happy, my goodness, he just got the bachelor's degree and, give him that kind of money, boy, he feels like, he's not married yet, he doesn't, So he goes on and cranks that stuff out and gets the result and, they give him a certificate. Okay? The company, of course, makes progress. Mm-hmm. Then, the school itself needs manpower. Okay? That's where the PhD comes in. Okay? Mm-hmm. First of all, the master's program is barely, at least in the technical area, is barely available in the schools they call black schools. Many people don't know that. Definitely the PhD is out of reach in the text, in mathematics, in engineering, in sciences. They don't exist in the black schools. Not here, not in the University of West Indies, not in the continent schools. They don't exist. Why? That marriage between the institutions and the Fortune 500 don't exist. because there are no Fortune 500 in the black world. Not zip. Jamaican Airways is not a Fortune 500. The finest airline to the Caribbean. It's massive. It's got all these heavy-duty planes and all that. But it's not a Fortune 500. It doesn't produce anything. It goes to Boeing to buy its planes. Bauxite in Jamaica is manned by Kaiser and Guyana and all that. It's Kaiser. But we don't do anything, and bauxite is the basis of at least the current airplanes that you use. The aluminum that comes from bauxite is perhaps one of the most strategic, piece of mineral. So Jamaica is sitting on it, so is Guyana and other parts of the diaspora, but they have no control over it. If they were to, then of course a Fortune 500 develops. A Fortune 500 is production companies, not services. That has to be clear.
Production company.
That's right. Production, they produce hardware. Okay? Not service. You can't say. That's not what we're talking about. That's Fortune 500 is manufacturing companies. Okay? So anyway.
And their primary product is military.
Oh, well. You ever heard about the military-industrial complex? If you want America to go to war right quick, try to mess around with Boeing. Yeah. The powers will be so automatic, and you'll be all, don't touch Boeing. Okay, but anyway, there's a lot more that you can, anyway, indeed, during Clinton's time, there was a war that was going on in Europe, between Europe and America, on a bid for the supply of airplanes. And it was critical that this country win that bid for Boeing. So guess who went to negotiate along with Boeing? Exactly. The First Lady was on the plane. Your own Brown, not Minister Brown.
Ron Brown?
Ron Brown. Ron Brown was on the airplane.
In 1996.
They went to negotiate for Boeing, who was in competition with Airbus in terms of who was going to win. We lost Brown in the process.
Yes.
Brown
was murdered on the way back. I mean, they said it.
I
know you didn't see that. I know the professor didn't say that.
By the greatest storm in Africa.
So,
By what?
The greatest storm in Africa. They said the plane cruiser was crashed, but they said the reason why it was, man, the greatest storm came up in Africa and it messed up all the navigation systems.
and the people there.
Then when they asked the people there, they said, what storm? What's going on? There was no storm. They used that as an excuse.
Yeah, well,
Yeah.
well, the brother from Texas had a similar experience. Leland.
Right, Mickey Lee.
Yeah, that's right. But in any case, anyway, so the fact that the First Lady went to campaign for Boeing, certainly would indicate what I'm talking about. So we don't have graduate programs, primarily because we haven't established this marriage between institutions and the Fortune 500 yet.
So Howard doesn't have a master's program?
Certainly not a PhD. There's some bare minimum masters because let's assume they even produce the masters and the PhD. The token that is only allowed them in the Fortune 500, and they'll kill me. Listen to that. It's so small that they can't do any effective master's or graduate program. They can't. So how that is covered is Well, we don't have qualified black youth to get into the program. So that's why Howard doesn't have it. Lincoln does not have it. Morehouse doesn't have it.
No master's program. Small or something.
It barely exists.
Mm-hmm.
Okay? You know, barely. Certainly no PhDs. Even if they have the authorization to produce, it doesn't exist, period. Okay? And so, because primarily when these students are produced, they don't have a place to go to get a job.
Mm.
So that's something that you have to think out first if you want that to exist. And so, you know, GAGUT now produces, you know, by grace of Almighty God only, it's at the position where tons of doctoral physicists can be written with GAGUT material. But if you don't have the Fortune 500, to, you know, where they can go to consult, and other universities that they can service, those PhDs will be useless.
Mm-hmm.
You're not going to train them here to get the PhDs here to go and fill up Harvard or MIT. You think that's feasible? I can produce within a year. I can probably give me 5 years. I can produce about 10 PhDs within GAGUT.
Mm.
Yeah, absolutely. But would Harvard take them all?
You will.
No,
It's original. You know how that is.
they're not going to take them.
Yeah.
That would, they don't want the character of the color then to change that drastically.
But they want to have, they always want to control something that nobody of their caliber understands.
But that's where we are.
Why?
That's where we are right now. If you go on the internet, there's a discussion going on from Brown, Cornell, and one of those California education universities, where a question is asked. I don't think I'm quoting it exactly, but it says, does anyone understand Professor Oyibo's work? That's thrown on the net. Okay? Does anyone understand Professor Oyibo's work? And so, you know, this guy called Bias, I think that's Hispanic or Spanish or whatever, picks up on that. So, well, I don't understand. He must be a phony. Right? Then the others pick up and they discuss and say, well, but hey, let's check this guy out. So they're checking and so on and so on. So, wow, MIT has a write-up on him. Better watch it. Don't write him off like that. Yeah, let's see. So they're looking at something. Anyway, the discussion is going on. Okay? And of course, Bias, you know, starting out with those things, he's choking. He's choking because when he looks at the facts, you know, and all that. Anyway, don't you know that they have my email? If they work hard, they can find out where Mr. Brown's living room is located. I'm not guaranteeing that you're going to let them in. but one way or the other, they know how to contact me. No, I'm out of the question completely. They're searching other people that understands the work.
I see. Yeah.
All right. So this is what we're talking about. A geometric, you know, okay? A geometric, okay? All right? Those who do, what do you call it, projective drawing can, you know, do some marvelous job. This is the kind of surface we're talking about, okay? In space, yeah. Well, you may have to,
I got it now.
okay, we have to move, okay. This is, okay, this here pictures of a rough sketch of a three-dimensional space. And indeed, it could be more dimensions, okay? And the universe is about this kind of space, okay? Because you can put a coordinate system to it, okay? You say that, okay? And of course you could, okay? You could do that and be able to, that could be, for example, X, Y, and Z. Right. Okay? You could put that to it. How you doing, Harold? Yes. You could fix that. Okay? And Z could be a dimension, which is changing as a result of X and Y changing. Okay? Z is the surface, say. And as X and Y changes, that would change. That particular surface would change. Okay? So then you can say that Z could be considered as a function of X and Y. Okay? Z is a function of X and Y. Okay? Or that could be, okay, a function f of z, okay, and z of x and y is equal to a constant. Okay? Or we will take this off and do that. X and y is a constant. That will give you this. So these two statements are equivalent. In the two dimension, you have, say, a straight line. Say x and y. Where you used to, y is equal to mx plus b or c. Okay? And so you could y minus mx is equal to c. Therefore, this becomes equivalent to y minus mx is equal to c. And this y minus mx could be called f of y, or rather, you can start with x, y is equal to a constant. Which is a part of this here. Because this and this are equivalent, and they're both equivalent to this. And it turns out that that's a convenient, this then becomes a convenient way to represent this. This is an equation of a straight line. A function of x, y is equal to c. They don't present it to you that often. And which is why most people miss the point, in terms of because you're working with this, which is nice, convenient, but And it really doesn't take any sweat to see that this and this are equivalent, all right? It's a matter of just a little rearrangement, right? And that leads to this, which in effect, the parallel in the two dimension is a two-dimension. The two-dimension will be that there, okay, which is the picture here, but in general, it can be more efficient to have it in this form here, okay? So that, whereas in a circle situation, x squared plus y squared is equal to c squared, okay? This is that form, okay? This is f of x, y is equal to a constant, because c squared is a constant, okay? This, of course, you can say this is y squared is equal to c squared minus x squared. Okay? Or that y is equal to square root of c squared minus x squared. Okay? You could say this. Both this, okay? Both this 2 or 3 are, they describe circles. Describe circles. They do describe circles. Either you have it this way or you have it that way. If I were to ask you, which form have you seen the equation of a circle more? Which one have you seen more frequently?
The first one.
The first one. See, that's consistent with this. Okay? That's consistent with this. Unfortunately, with the straight line, you probably say you see it more in this, right?
Yeah.
More in this than this.
I mean,
Okay. Yeah, you know that that's what it is, you know. But that little twist can make it different because unification theory, GAGUT, is about unification, generalization, common denominator. When you see this and this, that's a common denominator. Yes, sir.
I got it. Now, but what I didn't get is why y equals mx plus c is a straight line, and f as a function of x and y equals c is a curve. How do you tell the difference?
Okay. All right. This is a broader statement which includes this. Okay? In other words, this is a subset of this. In other words, because this can describe this and can also describe that. Okay, that's what we're saying here. So this form is a general statement. See, again, there is a sub-general and broader general and until you go into GAGUT, which is the full-blown generalization. Okay? You just have a little common denominator, which is geometry, and that galvanizes, that puts everything together. Okay? But within, there is a quantum subgroup, there is all manner of other subgroups, okay, depending on how you want to look at it. Okay? Which they themselves are broad enough, but you get to a fundamental building block, okay? Okay, in the quantum case, they look at the particle that is measured with the mass and the charges and so on and so forth, the characteristics, the properties, okay? The spins and everything else. Today they're talking about from the days of our great-grandparents, where atom was the most fundamental, okay, to Actually, that's not true. They knew about the subsystem of atom, certainly the protons and the neutrons and electrons. But going to quarks and leptons might be considered a step, below that. Okay. So there are these groups. Okay, this is a group in itself. Even the straight line is a straight line group as long as m remains a constant to be chosen at will. Whatever you like, you can choose this, and then to determine. I mean, this is a constant that can be changed. So is that constant that can be changed. So between the permutations between this, you have a whole group, tons of group of these straight lines. Okay.
But in the permutation, what would that entice then?
Well, in other words, if you take this as 1, for example, C could go from minus to plus infinity. I mean, okay, so
But
that's
it's only dealing with that at a certain rate.
right. Well,
If you're doing that's going from, let's say, horizontal, vertical.
yes,
The energy is going vertical.
yes,
That means that the only place it can go is up into the celestial area because that's developed into the circle, correct? So with the horizontal, which encompasses, I guess, the same parameters, the
Yeah.
same permutations, you're using both of them so that they can create some kind of single energy unit.
right. Remember,
And that's 0, wouldn't it?
well, again, 0. When you get cracking seriously with GAGUT, you will get to know about something called the relative zero. Relative zero. We had a very, very well-known professor who couldn't understand that. He had a major problem. One of the guys that still wants to steal GAGUT, but he had a difficulty with the relative zero, simply because we tried some of the realities here in terms of how a computer, for example, disobeys a very simple fundamental law of algebra, okay, which is that when you multiply and divide, actually, also, a number by an identity number, you get the same number. That's a fundamental theory. Okay? In other words, if you have a number A times an identity, or 1, what they call 1, is equal to A. That's the definition of an identity. Okay? Okay? So, and we proved last class that this is easily disobeyed on your calculator. We proved that to everybody. Yeah. Okay? So when you're using computer, especially when they're talking to you that computer is mathematics, that's a very serious problem. Computer is not mathematics. Computer is convenient approximation. Convenient, that's the key word. But you always pay a price for convenience. People never remember that part.
Okay, Professor.
Yes, sir.
So I tried that on my calculator. Okay, on the calculator, it will come out like that. But on the computer now, it won't come out like that. I tried it, on the calculator like he had the other day, it came out to 3.999999.
Yes.
But on the computer, it came out to 4.
It depends on the program that you use. It depends on the program that's been used to analyze.
That's number 1. Okay, that's a good point. Okay? There will be a number that the computer will be able to, because it's a matter of accuracy.
Right.
There will be a number that is challenging enough that your computer, whatever computer, any computer, will choke up on it.
Meaning what, Professor?
Meaning that you were just lucky that your computer was powerful enough and a lot of features were built into it that particular computer to not be able to deal with 4 over 3 times 3 to be not 1. I'm sorry, not 4. Okay? Yours, was able to do that. Okay? They share truth that the calculator is one level of the computer. Okay? The principle is the same. You know that if you could find this phenomenon with a small computer, you could find a number, okay, for the bigger computer that would choke the computer, that this will arise.
Right. But would it be significant if the number is the amount that is off is so small that it wouldn't make a difference? You see what I'm saying? Either way.
That point is not is point of concern, okay? But the point that is more serious is the fact that on one computer you may be able to get 4. On other computers you get 3.96. On other computers you get 3.8. On another computer, you get 3.999999 for the same answer. Says that those answers are not unique.
Well, but on
This exercise has one answer, that is 4. 1. So if your system is giving you all this numerous millions of answers, then the question is, which one is the correct answer?
But okay, now like on the calculator, it can't say on the calculator it can go so many places.
Yes.
But on a computer it can go more places. That's why we'll get a more
Exactly.
accurate.
But more is not good enough. You understand the point here? The zeros could vary, those kind of computers from 10.6 to, 10 to power minus 6 to maybe 10 to power minus 15. I don't know if that's possible. Okay? On the computers. You understand? In other words, the computer, the one that you're using, probably, counts this as 0. Okay? Whereas other ones that are not so sophisticated count this as 0. In some cases, 10 to the power minus 3 could be easily counted as 0.
Right. But I'm saying if you have such a small number like 10 to the minus 15,
Yes.
it wouldn't make a difference, would it? I mean, it wouldn't.
Right.
It wouldn't, like if you were saying something was you're off, the percentage that is wrong is 10 to the minus 15.
Yes.
That would say like that's not,
Depending on the application.
That's absolutely correct. But more seriously, the quantities, the quantum quantities, okay, for electrons and the subparticle that we're talking about are far smaller than this,
That's right, much smaller.
which is where this professor was having a problem. Okay? The quantities are, some cases, when computer is 10 to power minus 60, 67 or something like that. So you throw this away.
right. I understand.
So this is what we're dealing with here. So computer doesn't help you in this case. Absolutely doesn't help you, because computer will just record 0, 0, 0, 0 all over. And the way we're dealing with this here.
So you're
Okay.
saying that they don't even know what the real definition of absolute 0 is?
All right. So
Wow.
now, so
But there's such a thing as absolute 0, though.
Wow.
okay. All right. So that's what we're
They don't
dealing with.
know.
That's what we're dealing with here. Okay? So when I was trying to explain a relative 0, okay, to the mighty professor, he had a little problem. Okay? He had a little problem. Because this is definitely an absolute 0. This is not 0. It's, compared to things around it. So whoever was asking the question, the issue is about relativity. That's what the issue is, relativity. Relative zero, relative. When you do this here, you're just operating in this neighborhood. Oh yeah, that's you, my brother. You said, well, when you go far to the ceiling, okay, then you're talking about infinity, which is the opposite direction of the zero, okay? In other words, if you put 1 over 10 to the power minus 67 is equal to 10 to the power plus 67, okay? This is the kind of number that you might call infinity, but it's relative. If every number around it are those kind of numbers, then it's not infinity. So it's relative. Infinity is relative. Zero, you know, the kind of little number here, or there's a concept called a relative zero. Okay? You know, and when you look at the curves, you know, for the Grandify theorem, okay, the weak force field, for example, okay, has a range that is about, okay, the range is about 10 to the power minus 3, the range of strong force field. Okay? Okay? It's about 10 to the power minus 3. Okay? You know, so you're talking about 1 to 10 to the power minus 3. Okay? You could easily take this as 0. I'm sorry, this, you know, that at 0 because it's 10 to the power minus 3. If this was 1. Okay? Or if this was 10 to the power minus 3, say. Okay? Then this is in the neighborhood of 10 to the power minus 6, and most computers will already be called a 0. Okay? So you would say on that scale that, on that scale you'll be saying that if they, okay, you have that, okay, this is the gravity, okay, EM, okay, and let's say that this is the strong, okay, SF, okay, and this is the weak, okay, all right? The ranges are this value here, you know, basically about here, here, and here. Okay, here is goes, you know, goes out to go a little further. Okay, but this one here. So if you say that this is the strong here, this is 1, 0. This will be pretty close to 0. Okay, so you need a magnifying glass at this point here to really see the non-zero value for the weak force field. Okay? And so, you know, those are the kind of relative things that we're talking about. At the fundamental level, you got to be careful, okay? Because most of these definitions are things that analysts come up with. But because the universe goes from the smallest to the very largest, okay? Okay? For example, if you compare your size as a human being to the size of this room, you're small. Okay? Right? When you compare yourself, however, you know, to an ant, you're big. Okay? You're big, that's relative, okay? If you compare yourself to the city of New York, size-wise, okay, you're insignificant. We're all insignificant, tiny, okay? And suddenly if you compare yourself to the globe, the world, the earth, it's tiny, very, very tiny. And when you imagine that the earth, compared to the sun, is insignificant. And here you are bragging about this, you know, big earth that you live on, right? Except that when that earth compares to the sun, it is nothing, absolutely nothing size. Okay?
It takes 10 Earths to even get close to the sun.
Oh no, it's much more.
400, right?
80 Earths all in Jupiter alone.
It's much. It's simply insignificant.
You have sunspots as big on this planet.
It's much significant. Much insignificant. So that's the relativity that we're talking about. So it is in that context that an electron you can't even see. Okay? Certainly you cannot see the leptons and the quarks, right? So what does that mean? The theory says that leptons and the quarks are what the Earth is made of. And when you look at the overall size of the Earth, you say, well, that is too big compared to the leptons and the quarks. So on a computer level, you will say, well, the quarks don't exist. Do they not exist? Quarks do exist. That's what the Earth is made of. Hydrogen atom exists. That's what the Earth is made of. So you can't say because the sizes are relatively, big differences in terms of the atom being so small and the Earth being so large that you can write off the atom. Atom is real. You see, the size may not be, significant, but it's real because it's a building block. Okay? It's a building block for the bigger things.
Okay, I have a question for you, sir. Suppose that we use that situation where if we took an elephant and then you take 500 people and you got 2 airplanes. The elephant is going to be assigned to move 1 airplane and 500 people are going to be put on this airplane and pulled.
Yes.
So they're both creating motion, force, and this is all on a horizontal level. Now, what I'm trying to figure out here now is, will they both equal the same speed if they pull the 2 airplanes? You get one with 500 people pulling 1 plane and an elephant pulling the other. What would happen? Would it be relative?
And the mix.
If the forces amount to the same thing, because force is what creates acceleration. When you have a motion, the force is behind it. So if the force, like your F is equal to ma, okay? F is equal to ma. Okay, that's Newton. Okay? So let's say this is elephant, and this is F of the 500 men, okay? Human, H. Okay? It's equal to MA. Okay? Now, I'm sorry, I was blocking that. Okay, so it depends on the mass of that unit. Okay? And, if it's the same mass that is being pulled, okay, the same plane, okay, so they're all the same, okay, M is the same. So if these 2 are the same, then the acceleration will be the same.
Remember though, it might be the fact that 500 people the elephant may weigh more, or the people may more, or they might be equal in weight. This means this is just a situation where you haven't even did anything. You took 500 people and put them in there and random.
Yes.
Okay, so this is what we're trying to figure out, is that how does the energy fields connect so that matter is complementary?
Yeah, well, in respect to that, see, all this, as I proved, and I got to have you, that's the thing I want you to come away from the class with, is that all this is geometry. Yes.
That's just a movement now.
Well, exactly. See, because that's, for one thing, you're going to monitor that. You want to monitor that. Because, see, over here, you can normalize this here by dividing both sides by m. Okay? Okay, that will go. Okay, you'll be left with this quantity here, which is acceleration. Okay? So acceleration is a space-time thing. Okay, the rate at which you cover a distance. So it's acceleration. The mass is important, but only as a normalizer. Okay? You could do the same thing here. Okay? Okay? Again, you're talking about acceleration. So it's geometry as a primary thing. Okay? And you're going to look at that because that's what you really measure. You know, the thing was at one point at one time, and another time you open your eyes, there's another one. That's measurable, as you can see. Okay? So if this unit here is the same, this is equal to this, then that will be the same.
It depends on acceleration beforehand or after.
Well, of course, you know, the conditions will have to be, you know, you have to,
Flat.
yeah, it has to be, you have to prescribe a condition, you have to, you know, if they're all moving before that, then you have to take them into account, you know. But, you know, if they were started at the same time, and, you know, with the same conditions, okay, because if not, then you're going to have to add, you know, if this one had the previous acceleration, you would add previous acceleration, vectorial, of course, okay, a previous to that, okay, whereas this didn't, okay. So the bottom line is the total vectorial sum, okay, of that you're going to see.
Because all mass is doing is moving moving it toward the, in this case, the end of the axis at the same acceleration. Now, eventually, gravity is going to eventually determine what acceleration does here.
Yeah, well, you know, so that's why we have the F is equal to ma there. Ma is the total, you know, total in terms of vector sense. And so you're going to compare that. You're going to compare the accelerations once you've normalized this force here, okay?
See, don't mean I brought this up because that does show you basically how when you have metabolism in your body,
Yes.
it's based on the same situation of catabolic and anabolic because you're breaking down things so that you can build up into something else.
Yes.
So this means that you're using acceleration in this type of principle, you know, based on how much mass is consumed compared to how much mass is broken into energy fields.
Mm-hmm.
Now, what I would like to do with this is to create some kind of means where we can create the normality of pathology in the cell tissues, let's say, from nutrition to create these things, and this unified field theory would answer those types of situations.
Of course, of course. Well, which is why I made the earlier point in terms of, you know, the world is looking at you right now. What are you going to do with GAGUT?
Mm-hmm. Yes, sir.
And frankly, and that's also the issue of bauxite is relevant.
Yeah.
So is the issue of gold in Ghana. Okay? So is the issue of the oil in Nigeria, lots of other places. You know, so you have that. Most of the mineral resources come from your continent. So then the question is, and that's the basis of wealth, right? I mean, the gold is as close to, you know, wealth as you can get,
Yeah.
right? And so you have all the gold. The geography books that I see from the youngsters in this country shows Africa as having about 65% of the entire gold in the universe, in the world.
At one time,
Yeah.
65%.
No, that's a gold. That's the estimate of. We have 65% of the gold.
now.
Yeah,
That was only about, maybe at most 10 years ago.
10 years ago. That was in the geography books. So you have more gold than anybody else. So what are
A little
you
more than 10 years.
what are you doing? What are you doing living in the ghetto? You understand? So those are the things here, and so GAGUT is in the same situation.
You know, because I'm looking at this as I'm going to use this now for chemistry lesson here. I think chemistry is another form of diversity, you know, with what they call organic and inorganic chemistry. We're talking about two force fields. And every time that you eat food, your body turns and then processes and turns things from inorganic to organic,
Yes.
and vice versa. So we're dealing with metabolism.
Okay.
So with this in mind, we would say that this metabolism to me is a force field. In which whereby you have one side of this is catabolic and antabolic, and that's breaking down and building up.
Yes.
So if we use this situation, let's say, where we have certain organic ions,
Mhm.
can we produce these ions through the process of the unified field theory to produce,
Yes.
reproduce healing energy in the nucleons of cells, for example, in the neutrons of cells, for example, and you can create different things from solar energy into ions that affect it, and it deals with this thing directly, that the way fuel injection does to a car or something. It goes directly into the source of the energy field.
Yes, the answer is basically yes. And I say that because, see, the processes are governed by the four forces that were mentioned earlier. And whereas that had not been known up until GAGUT, now it is known. Okay? It is now known. So, except the one that God says, no, you can't do it. Okay? You'll be able to do that. Okay? God says you can't do this, you can. For example, what about altering the Earth's trajectory?
They may be mad enough to try that.
Trying to alter it. That's dealing with gravity. It's going on a trajectory, elliptical trajectory right now. If you have enough propulsive energy, you can alter that trajectory and begin to affect the solar system of the universe.
That's why
Certainly this solar system.
that's why they want to bomb it. If they drop those atomic weapons, that's what they want to do.
So that's the kind of thing we're dealing with here. It's heavy. People, when we got all this, people think this is some child. This is not child. This is not children. It's not children stuff. How you might be able to affect the trajectory of the universe, of the Earth, and the solar system. And see, if you don't know, you have no clue about what is going on, you might say, well, I don't know how that's possible. But now you know. And the whole world is watching you right now. Well, what are they supposed to do with this? And yet I can count how many people are here today.
Tapes.
And the young folks and these folks, they start talking about, does anybody understand Professor Oyibo's work? And it's like, well, no. I think I have an idea. Oh, no, I don't. So what we're going to do now? We got to go to him and beg to learn from him. We will try his book first. Right?
On top of that, some of them
Yes.
are
Okay.
free.
And then we could pull our own resources together, pull our heads together, and maybe we could, bypass him.
Yeah. Yeah, that'd be a problem.
Hey, does anyone understand Professor Oyibo's work? But, and of course the fear is, should they be successful, you have to be worried to some degree. Okay? If you think about Tuskegee experiment was rough,
Yeah, the transfer into the 80s.
I see. So, but anyway, so what we'd like to do is to talk about vectors. Okay? vectors. Vectors are very important. Vectors are part of that branch, is part of the branch of mathematics, okay, that deals with, whereas most things like scalars deals with quantities that have magnitude, and direction. Okay? There are certain categories of quantities that have not just magnitude, but also direction. And certainly, since if you move, this is, okay, that's a coordinate system there. And let's say this is 1, 2, 3, and then 1, minus 1, minus 2, minus 3. Okay? Okay, whereas going from here to here is the same distance, which would be what you call the magnitude, okay, as this one here, going from here to here. Their directions are different. Okay? They have the same magnitude, but directions are different. One is in the western direction, and the other is in the eastern direction, or whatever. Okay? They are in opposite directions. So, but if you look at this as two entities called distance, or distance is also called some other displacements. One is in one direction and one is in another. They have different directions. So you have the magnitude, which is the distance, and then the direction, which gives their orientation. Okay? That comes into application when you're looking at a curve like that. Okay? 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 Comes into application when you look at that. When you have a complicated shape, okay? It turns out that whereas, for example, in a three-dimensional case, whereas going from here to here is the same distance, which would be what you call the magnitude, okay, as this one here, going from here to here. Their directions are different. Okay? They have the same magnitude, but directions are different. One is in the western direction, and the other is in the eastern direction, or whatever. Okay? They are in opposite directions. So, but if you look at this as two entities called distance, or distance is also called some other displacements. One is in one direction and one is in another. They have different directions. So you have the magnitude, which is the distance, and then the direction, which give their orientation. Okay? That comes into application when you're looking at a curve like that. Okay? 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 Comes into application when you look at that. When you have a complicated shape, okay? It turns out that whereas, for example, in a three-dimensional case, a slope, which is the gradient of a particular surface, could be the same.
Wait, what is it?
This?
Yeah, what is it supposed to be?
Oh, that's the shape. I mean, that's a space, okay? Or a section of a space. You're looking down on it. You know, that's cut out from material or space. Okay, it's a boundaries, if you will. That's a boundary. Okay, it's a boundary. Okay,
It's not a flat surface, three-dimensional.
well, no, you can add a little more to it like that. Okay? You know, which gives it some depth. Okay, but it's crummy. It's not your regular, straight line. It's wavy. Okay, yeah, and over here you have something like that, and so on. Okay, and you can put some, in other words, it has 3 dimensions. Okay. So when you have stuff like this here, there are gradients. You know, you can look at the gradient this way, or by actually slopes. Okay, you know, this rise this way and so on. Okay, you could also look at a rise that goes that way, you know, that way and so on. All kinds of, dimensions. Okay, or directions. So what's happening is that in looking at that, you have various directions. Okay? So a slope within the proper definition could be the tangent of this angle here, theta. Okay? There could be also another theta there, okay, which will have a tangent. And it may turn out that these thetas are the same, but because of their orientation being different, they constitute different quantities. Okay? The slopes, which is the tangent of theta, okay, is, maybe the slope, okay, by definition. Okay? In one direction, the value may be the same, but the orientation might be different. And it will be showing the slope, slope simply means how much, if you go horizontally and you go vertically, would you be on the curve, okay? Okay? If you go this way and that way, you're going to be on the curve. You go again, okay, this is a curve that goes that way. You go this way again, and you go that way, and you're on the curve. You go here, and here, you're on the curve, that kind of thing. So, the slope then is really, about the angle here, okay? This angle. These are the slopes, okay, of the various points here, okay? You draw a straight line there, and the angle that makes with the horizontal becomes a measure of the slope, okay? That's what we call slope. So a space curve would have that. And as we mentioned in partial differential equations, these slopes have relationships with one another. Okay? The slopes, there's also, is in the 2-dimension delta y over delta x. That's what the slope, which in a limit as delta x approaches 0 is equal to dy over dx.
Now 0 is going to be at the point of measurement there.
You mean this 0 here? Or this 0? This the origin, which is called 0. But this 0 here is the relative 0, small quantity.
Correct.
You said slope
Right.
equals that piece right there.
Huh? Yeah.
Slope is equal to the limit that is.
Yeah, limit of the change in y, okay, if you take that y, say, and this is x, okay, or if you put another here, okay, that's y and x, okay, you go x and then you go y, okay, x and y, or dx and dy, okay, and from the geometry of this approximately, this is small, okay, it's like you only have a straight line from here, okay? And this small means something like that. So even though the curve is not a straight line, if this is small, then it's almost like a straight line, which is a relative concept. Okay? It's a very relative concept. That's why this requirement is made, that you are so small that there is no difference between the part of this curve here and a straight line that is drawn from it. Okay? So that instead of looking at this larger triangle, you're looking at the smaller triangle, which has most of the curves part on it looking like a straight line.
Right.
And it's true that you can take any curve and get that kind of approximation, and that's the whole basis of calculus, differential calculus. Okay? Limiting quantities. And the fact that you could make that as small as you want, it's that flexibility. You can make this very, very small, in which case that part of the curve will be a straight line, whether it likes it or not. Okay? You force it, and that's the beauty of mathematics. For you to make a point, you could do your definition. You could, say, look, if I can do this, if I can force the part of the curve to look like a straight line, then this is true. This is what I'm dealing with here. So it's a limiting process. Okay? Which is a relative, relative zero. It's not exactly zero. Okay? It's not exactly zero. It just approaches zero. Most kids either don't get that concept or it's not explained well enough to them.
Mm-hmm.
This delta x has to be small. That's what is meant by approaching zero. Then the question is, how small? As small as one. Excellent one. As small as one. Well, how is as small as you want? As small as you want may be different from as small as he wants. So, do you have a common denominator? You will just shake hands and agree to disagree. But you all have a ballpark kind of expectations. Okay, well, this is small enough. See, I can draw my line and it's right there on the curve, man. Okay, see? And the closer you get to, to this point, the better that approximation is.
Mm-hmm.
And as the closer you get, the smaller the change in x. Okay? So therefore, that represents a slope. And this slope forms the basis, or these slopes form the basis of partial differential equations, or differential equations. Okay? That's differential equations. Differential geometry is based on that. So who says there's a difference between differential geometry and partial differential equations? Who says there's a difference? No. Topology. What's your topology? What's topology? Well, youngsters will start dealing with graph theory. Graph theory. Wow. What is graph theory? And especially, I see the way that the subject is presented is so disgusting. I mean, it's like they turn these youngsters off completely. They don't give them any background. They're using some big words. What were you saying the other day?
Hamiltonian graphs, Hamiltonian cycle, K5 plated graphs.
Or other circuits.
You understand? These youngsters are overwhelmed. They're completely overwhelmed.
With no explanation to what or
Okay.
why we're doing this.
And so then what happened? They feel like they've been punished. And frankly, it's not, the teachers feel like, well, look, they're showing off or whatever they're doing, I have no clue. You understand? You're not helping the youngsters with those bogus words, okay?
Especially when one of the people who claims that they're such a master of mathematics, you ask them a simple question about differential equations and they've never seen a differential equation before.
There you go.
And yet they're teachers.
All right. Graph theory. What's graph theory? Well, the name is supposed to be descriptive of what the subject is. Graph theory. Right?
The theory of how you compute
Thank you very much.
graphs.
Thank you very much. Did your teacher ever tell you that?
I can take it, yeah.
That's a smart kid. He didn't. He was watching, keeping it up.
You're telling me that today's modern math teachers have never seen a differential equation. That what you said?
Oh, they put down.
One of the professors at my old university He was graph theory teacher.
Without the win?
No. But it was another professor. I don't want to get into names right now.
Right. Give it.
Yeah, because
Yeah.
I presented a differential equation to him, and he basically did not know what it was. He didn't know what it was.
And they called it the dinosaur, something like
You
that.
said that people
Oh, I know
practice
what that
that
is.
as full, I mean, it's going to be like.
I know that
extinct.
is. You mean,
That it's basically like a dinosaur mathematics.
Dinosaur mathematics. Can you
I
imagine?
know you're talking about.
Mr. Complex and Dallas.
Yeah, I know you're talking about immediately.
Well, they're saying that this kind of thing is dinosaur
I know
mathematics.
talking about.
Okay? But I've been talking this year, and I can get your response, and I'm feeling energies from you about, what, I mean, about the practicality of this here, right? I'm talking about slopes of this, thing here. Okay? I'm getting response, right? So I know that you're coming along, you haven't seen everything yet, but you're coming along saying, yeah, well, the slope is, how much horizontal you go to get a vertical in order to be on the curve. That's what the slope is. And if you move close enough to the starting point, you could approximate the curve by a straight line, which is an approximation. Okay? And you can do that for every point on the curve. So therefore, you can talk about a slope, something like this, for every part of the curve. Now, so, like Mr. Brown said, graph theory is supposed to be about a theory of how you draw graphs simply. That's all it is. You draw graphs. In other words, how you draw geometric figures. That is graph theory. Okay? That's all it is. But before the kids can settle to get a sense of what it is they have to study, they're blasting all this heavy-duty stuff, congestion, this, and, the kids are lost. The kids are lost. A simple theorem is presented in such a complicated, kind of thing. So then they go to, so topology, topology comes from graph theory. Okay? What's topology? You ever hear about map making? Map making. What are you doing map making? Okay?
That's topology.
Topology. Well, okay. You want to know the map of the of the Earth, Mother Earth, the countries and continents and the waters, and mountains, and all that. Okay? You may have walked around, or sailed around, or traveled in the cars, or airplanes. So you visualize things. Okay? You have your plan views, and in some cases you have some elevation. So you look at that and you said, this is what I saw. You put up your table and your paper. You say, well, if I was going from New York, this is the route here. I want to draw this boundary here of a state called New York State. It goes like this, and like that, and like that. So what you've done by the time you got that enclosure is put the outline of New York State on a paper. On a paper, a piece of paper. You've drawn the graph of the boundary that constitute New York State. What does that mean?
You have a rough outline of what the city looks like.
You've done topology. That's topological map. You have drawn, it's not the Earth, it's not the real New York State, but you've gotten a picture of it on the paper. That's topology. Now, in geometry, what you've done is you have transformed the physical space called New York State into a different space on a piece of paper. every point on that drawing has a corresponding point, a corresponding point on the boundary, real boundary of New York State. That's called what is called in functional analysis a one-to-one correspondence. Every point in New York State will correspond to a point on your paper, otherwise you didn't draw the thing right.
You might call that an isomorphism.
Where color what?
There you go.
Isomorphism.
Isomorphism. Somebody throws that at you in the middle of what we're talking about. What does that do to you? Isomorphism, man, that's what you, you understand? So, man, people are going to be pissed and so discuss what the hell is isomorphism? You know, and you get lost. You're transforming every point in the boundaries and the domain of a space called New York State onto a piece of paper, which is a different space. And it is scaled such that every point on the reality of that location is represented on your drawing. So you are doing a graphing, okay, which is, you want to call it topology, right? But you are doing a geometric transformation of two spaces. So whether you call it a geometric transformation or topology, is there any difference really?
No.
Is there any difference? Call it topology, topological map, or a geometric transformation, they are the same thing. You consider drawing a graph, but a graph is a representation of something, just like I did here. This is a representation. So I'm doing topology here, okay? All right? Because there is, wherever I'm getting this picture from, whether it be imaginary or real, it's a different space. I'm just putting it down here, okay? I'm putting it down here from something that is either imaginable or is real. But there is a one-to-one correspondence between any point on this and that my imagination. So it is transformation, it is geometry. Don't let anybody kill you. Geometry. Okay? But you have this things to worry about, because if you assume that you can sketch this for every space or every set of spaces in the universe, okay, then you want to get a sense of what are the dynamics of this crumbing surface here. Okay? Are there some features of it that you can put down? And that usually comes up in terms of a partial differential equation. Okay? Somebody might look at such a shape and say, gee, the slope in one direction plus the slope in another adds up to a constant. Okay? So, you might have phi, okay, x plus phi y is equal to a constant. That becomes a partial differential equation.
Can I just ask you a question?
Yes, sir.
Now that phi x,
Yes.
now you change the language on me a little bit there. Why'd you put that zero and that line through it, call it a phi x?
It's a symbol to.
Why did I have you call you minister? Why put a hat on you and I call you minister?
Okay, so it's arbitrary?
Yeah, exactly.
Oh, it's just what you want to name that point.
That's right. I told you about the flexibility.
Okay.
Thank you very much. That's an excellent question. This is the real problems, because if you're able to go past some of these things that are basic, okay, nothing can stop you anymore. Because the rest is a simple human reasoning, which everyone, especially an African, has. Tons of it. Okay? So nothing can stop you. So it's like the language barrier, okay, you know, in terms of, you know, I mean, it's awesome that you asked that question. What does phi have to do with this? Okay? So, phi, if you don't like phi, use m. Okay?
Mm-hmm.
If you don't like phi or m, use t. Okay? Tx plus ty, okay, is equal to c.
Mm-hmm.
Okay? Or f. Okay? Fx plus fy is equal to c. F or phi, okay, is representing this curve here. Okay? As we said before, this curve here could be f of x, y is equal to a constant. We said that. Okay? And we gave an example of a straight line where, you know, that would be f minus mx is equal to c. Okay? That will represent this. Okay? But this one that is chromier would fall into this general representation here. F of xy is a constant. We comfortable with that? Okay? This came from here. This is a special case of this. This one here is a special case of that one. Okay? So this, you don't know what the thing is. In fact, if you get over here and get wild, like that. Okay? Crummy. But it still will, you know. And so f is a constant, represents this here. All right? So, or t or m. So its slope, okay, it is said that somebody observed the slope, and that's an observation. The slope of that curve in x direction plus the slope in the y direction adds up to a constant. That could be an observation. So now, this gives you a hint on how to find this f of x, y, which in effect will give you the actual equation that will describe this function, which means that by the time you determine f of x is a constant, you'll be able to go like this. You choose x, and then you go y, you'll be on for every point of that curve. Okay? Which is clearly a geometric exercise. But that's where all the functional theories, you know, come from. Okay, when you talk about topology, okay, now you're talking about the transformations, and you know, when you're talking about the transformations, you got to worry about, you know, some points in the domain where this shape here will have some problems, will have some kinky, some crummy behavior. Okay, you know, maybe this goes like that, say, okay. This is a very difficult thing to deal with. This is a very sharp. If you have a point like this, you got to make a note of that. And in the topological situation, you got to make a case about this point here, which will correspond to this x here.
But wouldn't they make it now, I mean, discontinuous?
Yes, that's part of it, is discontinuous. So when you're talking about your compact space and all the other stuff, okay? So now you got to worry about dividing this into maybe two kind of spaces, okay? The ones up until this point and another after that point. And you treat this like a special case, or this domain has a special case. So you have like 1, 2, 3 kind of spaces. And space is just a domain, some kind of, you know, geometry, some kind of area or a volume, you know, containing points of geometry. Okay? So the key then is how to determine this. And this would help you determine that. This or any of this here, depending on what symbol you use. Okay? All right. So if we have that, let's say we have this here, the shape that is described by f of x and y is a constant. And once you've understood that, you can see how f of x, y, z is a constant would give you a three-dimensional relationship, which will give you z is equal to z as a function of x and y. Okay, that's a three-dimensional situation.
So that'd be C or 0. That's it.
That could be c. Okay, and 0 is a special case. Okay, yeah, since 0 is a special case. So from there you get this. Okay, just like from here you get yes. From here you get y is a function of x. Okay? And there's nothing unique about choosing z as a function of x and y. Technically, you can say y is a function of x and z, and all the other combinations. Okay? But, having said that, how do the vectors come in? Okay. If we take df, okay, is equal to fx dx plus fy dy plus fz dz. A total change in f, which meaning that curve there, would be the partial change with respect to x times the change in x, plus partial change with respect to y times the change in y, and the partial change in z, multiplied by the change in z. Okay? This is perhaps the most important part, most fundamental part of partial differential equations. Okay? Where this, of course, is d phi dx, partial with respect to x, and so on and so forth. That is df dy, okay, and df dz, okay? Okay, partial, meaning as you're watching this change with respect to x, y and z are kept constant. That's the meaning. And here, x and z are kept constant. And here, x and y are kept constant. Okay? That's a broad change. Okay? Now, so, there's something called a gradient vector for that f. Okay? Gradient vector v. Okay? Which is df, okay, dx I plus df dy j plus df dz k. I'm sorry, what? This k.
No, I just can see it all.
Oh, yeah, I'm sorry. We'll see. Pull it here a little bit. I don't make it, have a problem? Okay, so we're good, right? Which can be written as, this is called a gradient, this also can be written as this. We bring this I back, d dx plus j d dy plus k d dz f.
Now, can I ask you, just
Yeah,
help me out a little bit?
yeah, sure.
Now, with all the rest of it, we've had a draft, or we've had a drawing that represents a form, you know, so forth. But where can I pick these
Yes, this
numbers in correspondence to points on something?
Yes, well, what we deal with here, this limit here, which is the change in y, change in x, the limit of that as delta x approaches 0.
Okay.
Okay? It gives you this. Okay, that's where the y dx comes from.
Okay.
Okay, and y in this case, you know, could be represented by this curve in general. Okay, f could represent the y in that case. Okay, so you know, so if that is the slope, the change in, or rather, this is the curve. The change for each point on the curve of f, okay, as x, change in x approaches 0, the ratio will become that. You know, if this was f, okay, then what you get is that also becomes f. Okay? Now, that is if it is one dimension, only x. If it turns out that it's a multi-dimension, okay, all right, there's another dimension over here, you could do the same thing for, take a limit as delta y approaches 0 of change in f over change in y, okay, which would be df. Of course, it will be partial, okay, we call this that, okay, partial in the sense that it's the same thing as before, except that you holding x and y, x, y and z constant. That's why we use this symbol instead of the other symbol we have in the case of one variable, okay? You want to be able to identify them. So df over dy, okay? And similarly, limit of, that ratio, change in f over change in z, okay? As change in z approaches 0, it's also df over dz. That's where this came from, okay? And so when you want to look at the total change, okay, in that space curve, this is the general formula that adds up all the, because all these are independent changes, okay? These are independent. So if you take that rate of change in the x direction, which is this one here, multiply by the change, arbitrary change in the x direction, you get a component from the x changing. Similarly with the y changing, and similarly with the z changing. So there is a quantity, and this is defined for a reason. The v is eventually called the gradient, okay? Gradient, grad of f, okay? That's what it's called. It's called the gradient of f. Equal to gradient of f. Okay? Which is a vector gradient or gradient, gradient of, or vector gradient of f. Okay? It's vector because you have I, j, and k. You know that these are the slopes in the x direction, the rate of change in x direction, rate of change in the y direction, and rate of change in the z direction. What happens if you make a vector out of those three changes? A vector is something that you can represent, like a coordinate system, okay? Right? You have a direction here, you have that there, and you have another here, okay? So, let's say you represent the phi dx here, okay? And the phi dz here. And then the phi dy, okay? Over here, okay? Now, even though they are individually, looks like they're scalar, they are independent. Why are they independent? These changes are independent in the sense that when you are looking at this rate of change here, you said that x and y and z are constant. They're fixed. So that has nothing to do with y and z. Okay? You know, while you're evaluating this, this has nothing to do with y and z. Okay? So as you're doing this dimension here is not, he doesn't know about it. There's no influence in it at all, instantaneously. Okay? When you go to y, however, okay, x and z are not aware. They fixed, they kept constant. They're not contributing to it. Then you go to the phi, the f, the z, then is y and x. So those kinds of quantities are considered independent. They're considered independent. And because they are independent, you could represent them in three orthogonal, what you call orthogonal directions. Okay? They are independent. And that's the basis of your functional analysis. Okay? X, Y, and Z are supposed to be independent. You can change one at you know, in other words, you could go along this direction here without affecting this here. That's the independence. Okay? You could go here without affecting here. You just keep on going. You don't touch this at all. Similarly, if you're going here, you don't have to, you know, this is not touched at all. Okay? And if you are going over here, these two are not touched. Okay? So they're considered independent. So that forms what you call an orthogonal triad. Okay? An orthogonal. Orthogonal means that they are 90 degrees apart. Okay? I mean 90 degrees. Okay? They don't have impact on one another at all. Okay? This one here would be similar. Okay? 90 degrees. They are mutually orthogonal. Mutually orthogonal. Okay? Mutually orthogonal. Orthogonal. Okay? That's a terminology. But orthogonal means that they all have 90 degrees, you know, as angle between them. Okay? Because the change in this does not affect the change in that. Okay? So that means that you could represent them, their overall impact, by a vector, okay, that has a unit value in the x direction called I, and that this here, another vector, that has a unit here called k, a unit vector. I'm going to get into the unit vector. And over here, you have another one that has a unit vector, j, in this direction. So therefore, you could consider a quantity that is a vector summation of those vectors. This becomes a vector, okay? This multiplied by this becomes a vector, okay? Even though this is a a scalar. Okay, this one, you know, it's only along this direction, but you can make it a vector by multiplying it by a unit vector in that direction. Okay, which is J df dy, J df dy. That's one vector. Okay, all right, and then you could look at this times I, which is df dx I. Okay, and then the one in the k direction is df dz times k. So you can look at the vector sum of these slopes. You just adding the vector effect of these slopes. What does that mean? Well, it's something that you just looking at, okay? You don't know what it means yet, okay? Is this useful? Because in math you can define anything, you can call anything anything you want, okay? But does it have any use? Okay? This vector here, okay, you could conceptualize this vector here. You know, a vector is anything that's represented along this, you know, thing here. And you could take any quantity, which is a function of x and y, multiply by the unit vector. This is a unit vector, meaning that it represents a direction, okay? It has a unit by that is, it's like what you call a unit, that like pennies that you use in counting something. A penny counts money. A penny is like a building block, okay? I is like a building block, okay? So you want to see the vector in this direction, you take the magnitude and multiply by the unit vector. That gives you the vector in that direction. Okay? This is the vector in the y direction, vector in the x direction, and vector in the z direction. When you add them, you have a total vector, okay, in this space there. Okay? In other words, you could transform, you know, and get this plus that, or transform it somewhere, and you could add them. Okay, this will be a summation, you know, of these three vectors.
Mr. Martin, again, you said the vector in that direction times
The unit vector.
The unit vector gives you the direction.
No, the magnitude in that direction, the magnitude. This will be the magnitude, and the unit vector will give you the total vector in that direction. Okay, okay. The magnitude of the vector multiplied by a unit vector in that direction will give you, it's like I said before, the pennies that you use to count, okay, you know, the monies, okay, $1 has 100 pennies, okay, okay, 100 pennies, you know, is $1. So you know, the 100 P is equal to $10, okay, or cents, okay, is equal to, so this is like $10. So this is like the unit that we're talking about. This is equivalent to the J, okay, it's the unit. You know, you either call pennies or cents, okay, is equal to that. So this becomes a unit by which you count the content of this $10, okay? Mm-hmm. So it's one unit, okay? Right. That's what the J is in for the Y direction, and that's what the I is for the X direction, and that's what K is for the Z direction. You got to have, yes, go ahead.
Does that unit include, is that a summation of the mass?
That's simply a summation of this animal you call, you know, in other words, vector has this property, okay? Like we said before, it has magnitude. In this case here, that's its magnitude in this direction, okay? And direction. The direction is signified by the J, which at the same time is the unit in that direction for measuring it.
Okay, all right.
All right? And the same thing with the other directions. Now, once you have put them in those terms, now you can add them. You're not adding apples with apples, okay? Because this is a vector, and that's a vector, and that's a vector. You can add vectors. They're the same quantity now. Because you take this thing multiplied by its unit vector, and so on and so forth. This is called a vector addition. And it gives you something called the vector gradient of the function f is equal to a constant. Okay? So, again, most of the things that we define in math are motivated by application. And we're going to see, if this has no use, you can define it all you want. It will just melt away. But let's see what the use of this is. Okay?
One question, is any particular way to write total vector in a particular direction? Like if I want to say df dy times j would equal to something, how would I write it? Is there a special way of writing it, or just write it in words, or what?
Well, you could represent by something, it doesn't matter. In other words, you want to represent this by another vector. You could call it anything. Huh?
It's a piece of cake.
Okay, yeah, you could piece of y, whatever, or j, or something, Yeah, you could represent it, but provided that you use a vector notation. You could do that. Okay, you can call it anything you want. But you got to allow yourself opportunity for clarity, consistency, easy visualization. That's so. Y, it's just a represent that. I represents the unit vector in the x direction, okay? And j for y, and k for z, okay? So most people have come to use that. Yes?
How does 106 equal $10?
I'm sorry, $1. Yes, that's $1. Thank you. Yes. Yes, you have to add another. Yeah, that's $1. Okay, 1 unit here consists of about 100 pennies. Thank you. Okay. So we have defined this here. As long as they're vectors, we know that we can add vectors like this. Okay, especially they're orthogonal. Okay, means that this is independent of this and this and so on and so forth. So let's look at that. And it could be further written in this fashion here. That's getting a little more sophisticated. Okay? Because now we can call this something. We're going to go over this enough times for people to really begin to get a sense of it. Okay? This quantity here can be called something, okay? This can be equal to gradient of that, f, okay? Where del, this is called del, okay, operator, is defined as I, okay, d, dx, plus j, d, dy, plus k, d, dz. Okay? This becomes a definition. Okay? That's a vector. It's called a del operator.
Let's just look up. Okay.
Del operator. Okay? It's called del operator. Del operator.
Is that the F?
Yeah.
Yeah.
That
It's a del operator.
yes, because that's an operator,
Okay.
which is operating on F in this case, right? The V would clearly be a del. This is V. Okay. Okay. So now we're going to see what we could do with that. What happens if here you have a direction, okay? You have a direction. You could look at this here as you could look at this curve here from a polar coordinate kind of situation. Or, not so much a polar coordinate as it is what they call a radius vector. Radius vector means that if you take this point here, for example, you could start from the origin, which is part of the polar coordinates, okay? To draw a line from here, okay, you need 2 points to draw a line, okay? So you take this point and that point in the curve and you draw that. This here becomes a radius vector, R.
Is the sum of all these vectors?
No, it's a vector that originates from the origin, okay, and ends on that point on the curve, on the space, on the.
So 2 points, 1 point from the origin and 1 point somewhere else.
Yes, you take any point on the curve, and you go from the origin to that point, and you draw a straight line that is called a position vector. Okay, position. It's getting crummy here. No, position vector. Okay, R becomes a position vector. Okay, R becomes a position vector. Call it a definition. Okay, position vector. Okay, whereas you could call this described by, x and y. Any point on that curve could be determined by x and y. You go here and you go up there, determines the point.